Okay, so in the remainder time, we'll talk about another search strategy called the depth first search, DFS. Okay, so idea speaking, high level idea, it has some similarity with BFS, but then because the order that exploring nodes are different, has different properties. Okay, so today we're just going to, in the remainder time, we'll just talk about what is DFS and what is its algorithm. And next time we're going to talk about its properties as well as how to use it to, for example, to solve the so-called topological sort problem in the DAG, in the direct acyclic graph. Okay, all right. We just talk about the BFS where on the high level, you starting from the source, you start to discover other nodes, and then when you explore those nodes in BFS, we always choose the oldest pending nodes, those that we discover first to explore and expand. Okay, now, and because of that, you basically first explore as wide as possible before you go to the next layer, namely go any deeper. Okay, all right. Now the so-called depth first search. Okay, instead of choosing the oldest one, the one that you discovered earliest. Okay, now we're going to actually immediately always explore the newest one you just found. Okay, we keep exploring the new one you found, and then keep finding new nodes as well, discover newer nodes as well. Okay, and consequently, as a result, it kind of keep going deeper and deeper. Okay, you find a new node, immediately find one of its neighbor, go one layer down, and then further. Okay, so that's why this is called a depth first search. Okay, all right. So more precisely, okay, we are given the graph G and a source node S, just like before, like in BFS. Okay. Oops, this is the depth first. Okay. And like before, all the nodes have three types of status: undiscovered, pending, and visited. Okay. At the beginning, all the nodes are initialized as undiscovered. Okay. Once we find the node, discover a node, we change its status from undiscovered to pending. Pending means that this node has been discovered, but we haven't finished exploring, processing all its neighbors yet. Okay. And now at each step, we take the newest pending node instead of the oldest one to explore. And after we explore all the undiscovered nodes reachable from this node, okay, when it come finish exploring all its neighbors and wherever they can reach, okay, we now mark this node to be visited, okay, and we'll repeat till there's no more pending nodes to explore, okay. So the only difference with the BFS is this, okay. All right. Now, algorithmically, what does this mean? Okay. Intuitively, for us to be able to, in BFS, since we want to extract the oldest pending node, that means that we needed a data structure which is first in, first out. Okay. That is the standard queue data structure. Okay. Here, intuitively, we want to extract the newest pending node, namely the first, those that are added to the pending list the earliest, the first in, actually will come out last. Okay, so this kind of philo, the first in last out data structure, is essentially can be done using a standard stack data structure. Okay, but the idea is actually much easier to be implemented using a recursive algorithm way. Okay, the stack is implicitly done through the recursion. Okay, in particular, what do I mean by that? Here's the algorithm for DFS. It actually is very simple. Okay, let's look at it. So the input of this algorithm is the graph, a node, current node that we're exploring. Okay, and the status of all the nodes, and the status if it's at the beginning, if it was not initialized, if you don't have it, then you set all the nodes to be undiscovered. Okay, but in general, the status will be passed on to the core of this procedure. Okay, okay. Now, you explore this node, you mark it as pending. Okay, then for each of its neighbors. So now you're going to explore this node U. Okay, then for each of its neighbors V. Okay, you check If V was not yet discovered yet, okay, then you immediately you go to call DFS. You first finish processing this one. You explore this one, okay? And after you finish explore this node, you come back, you go to the next neighbor of U, and so on, okay? And after you finish processing all the neighbors of U, you come back. So after all the neighbors of U are done, come back and you set the status of U to be visited, okay? So that is what the algorithm is doing, okay? So we're using the recurrence to do the stack. As you will see here, once you discover a neighbor which is not yet discovered, you immediately perform DFS continuously from that node. You finish exploring that node first before you come back to U, okay? All right, so let's use an example to see what this means, okay? At the beginning, let's say that I want to explore this graph through the nodes S, okay? And again, we follow the convention that all the neighbors will always visit them in increasing order of their labels, okay, alphabetically. So, all right, what do I do? We put this node as pending. So this node right now, we set its status to be pending, okay? And we start to explore its neighbor, okay? The first neighbor is A. What do I do? We immediately now say, I'm going to now explore A now. So that means we now call DFS GA. So everybody else, what I don't mark is still undiscovered, only S now become pending, okay? So now we're going to call DFS at A. What does that mean? That means that I'm going to set the status of A to be pending. And then I explore neighbors of A, okay? The neighbors of A is, there's only one neighbor right now, that's E, okay? That means that, so I explore neighbor of A, and that leads me to E. And our algorithm says immediately, let's explore E first, okay? So now I immediately call DFS GE, okay? So when we explore this one, we set this node to be pending, and then look at the neighbors of E, okay? Now, neighbors of E, I have only one outgoing edges from E that leads me to H, okay? So now we discover yet another new node H. So we have to, the algorithm says, okay, I found a new node, then I need to now explore that node first. I always explore what I most recently found, okay? So now we're going to explore this node H. And the H status is changed to be pending, okay? All right. And when I explore H, I look at its neighbor. H again has only one neighbor, which is, oops, which leads me to G. Okay, so that means that, okay, we need to explore G now. Okay, because always, whenever I discover a new node, I go deep, I go explore that one first. So from G, so from now we found G, we explore this. And when we explore G, I look at its neighbor. And then G has the, remember the order was go alphabetical. So first we found F. Okay, so now continuing, going to call DFS G on F. And when I do that, this one become pending. Okay, and then I discover neighbor C. Okay, so now I have to call DFS G on C. And now C become pending. Now I need to explore the node C. So when I look at the node C, I have one neighbor, is E, but the E is already discovered. I don't do anything. So I don't do anything. Okay. Then I have another neighbor, which is G. G is also discovered. So again, I don't do anything. So that means that now C is done. We finally finished the processing C. Okay, because I explored all its neighbors. There's nothing to do there. Okay. So now at this point, we change status C to be visited. Okay, so this one become visited. Okay, so that means that this is done. This call is done. So now when this call is done, it go back to the one that calls it. So it go back to the exploration of F. Okay, now we look at F. F doesn't have any other neighbors. So we're done exploring F as well. Okay, so now we set the status of F to be visited. And this to be visited. And F is done. That means this function is also done. When this is done, what do? We go back to the function that calls this. Okay, that is the function when we're exploring G. Okay, and at the G, I still have new edges to explore. We still have another neighbor, which is I. So now we discovered I. Okay, so now at this point, I need to call DFS, G, and I. Okay, and when I'm exploring I have an edge which is going to H, but H is already discovered. So I doesn't need to do anything there, and I doesn't have other neighbors. So then exploration of I is finished. Okay, so we finished the processing I. So its status changed to be visited. Okay, and then we're going back to who called me. Okay, so and this will basically essentially go back to G. Okay, so oops, I should use the red color to be consistent. So this one also go back here. Okay, now at G, I don't have any more neighbors. I finished exploring all the neighbors. That means that we're finally done with G. So the G status previously was P, now that one changed it to be V, and then we're done with, so now status of G is visited. And the whole thing is done. We go back to H, okay? And at H, sorry, at the G, actually, I forgot to say at the G, we also discover H, but then H is already discovered. So at H, we also don't see any new, we also don't see any neighbors, new neighbors, okay? So H become change to be visited, and we go back to E, okay? And then at E, again, I don't have any other nodes to visit, so this one change to be V, and then we go back. So H goes back to E, and the E go back to A. Okay. Now at this point, we are A doesn't have any neighbor, so A goes back. So all of this change to be visited, and it goes back to S. Okay, and then at S, now I need to explore the other neighbors of S, which is C. But C is already visited, so there's nothing need to do. So I finish exploring neighbors of S. We are done. So we put S status to be V. Okay, then this algorithm finishes. Okay, so this is how this works. Okay, so in fact, let me mark all the edges where we kind of called a new called a recursive call. Okay, so from S we lead to A and get into recursive call to A, and then from A to E, E to H, H goes to G, and then G goes to F, and then G also go to I. And then from F, we went to C. Okay, so this is the order of who, when we visit the one node, we called the DFS on another node. Okay, now after this, we note that B was untouched. B status remains to be undiscovered. Okay, and this is not surprising. In this example, B basically is not reachable from any of the nodes. Okay, so its status will be unvisited. Okay, all right. What this says is that basically by calling DFS at node, start with the DFS at S, we visit all the nodes reachable from S. Okay, in this particular case, because B is not reachable, just same as BFS. Okay, this node B is not reachable. That's why we never touched it and status didn't change. Okay, questions? All right, okay. And it's also worth noticing that the order of pathway. So for example, at the beginning, I'm going to use a purple color. From S, we go to A. From A, we go to E. From E, we go to H. From H, we go to G. And from G, we go to F. From F, we go to C. This is the initial. We keep going deeper and deeper, okay? And then from E, after finish C, we trace back, go to F. And from F, we trace back to G, and then we'll visit the I again, okay? So as you see here that at S, instead of immediately find all the neighbors of S, go as wide as possible. I keep going, finding new nodes, so I go as deep as possible. Okay, that's why this is called depth first search. Okay. All right. As I said, DFS would visit all the nodes reachable from the source node that you started first, called DFS first. Okay, and if the input graph is undirected and connected, then they would visit all the nodes. Otherwise, it will only visit those nodes in the same connected components as the source for undirected graph. Okay, and similar to BFS, if I want to visit all the nodes in the graph, then I need to call this full DFS, okay, which require us to restart from undiscovered nodes after we finish exploring one source node. Okay, so here is then a code to do that. So at the beginning, all the source, all the nodes have status undiscovered. Okay, then same as the full BFS, we just start from nodes one by one in order convention, alphabetical order, or the increasing order of the label. And as long as this node is yet undiscovered, we call DFS and start to explore the graph starting from this node. Okay, note that this would then explore all nodes reachable from the current node. Okay, and then we come back and then we continue and check if you find any other node still not reachable, still undiscovered. That means that it was not reachable, hasn't been visited before. Then you start DFS from that node. Okay, so in the previous example, in this example, after we finish core DFS on S, we notice that B is still undiscovered. So then we will the full DFS will then call DFS on the node B to explore that as well. In this case, B can only reach A, which is already discovered, so there's nothing, and then we're done. Okay. All right. This is the complete code for this. Okay, so just putting these two pieces together. Okay. Okay. Time complexity. What is the time complexity of this algorithm? Okay. Well, again, similar to BFS, okay, we want to, it's hard to write out the recurrence or anything, even though that we have a recurrence algorithm here, okay? So it's easier to count, okay, what the total number of operations in the global manner, okay? So when we look at this DFS algorithm here, okay, when we look inside the code, okay, now, the initialization, this would only be done once. So this initialization takes time because you have to go through all the, so this takes time, which is the order of V, okay? You have to change it, set the status for all of the nodes, okay? Then inside the DFS, what do I see? Well, for each of the node, we're only going to call this DFS visits this once, okay? We're only going to exploit once. So we'll, and inside of this exploration, we basically have to spend the for loop, okay? Forget about the cost here. So this cost we don't know, okay? So ignoring this cost, the for loop will take the degree of this node time without counting the recursive cost. So ignore this. Then this for loop would take order of degree, okay? Because we need to essentially, the for loop is basically that we're going to visit every edge going out from U once, okay? So the total cost of this for loops, okay, across all the DFS course, okay? So let me just write it here. The total cost of the for loop in DFS procedure across all course of DFS, okay, is sum of the degree of all the nodes U, where U is in V. Why? Because we can only call DFS exactly once. So every node will be explored exactly once. We can only call DFS on a specific node exactly once, okay? And when we call BFS on that node, the for loop takes degree of proportional to degree of this node, okay? So the total time ignoring the recursive call is such this. And this, we said that this is essentially means that we're visiting every edge exactly once for direct graph or exactly twice for indirect graph. So this is basically order of E. Okay, so this. Okay, so the total cost of all the for loop takes time E. Okay, and the recursive call is handled by counting the total cost across all the DFS. Okay, and as such, the final time complexity is basically V plus E. Okay, again, a quick way to think of this is that if you look at this algorithm, we are visiting each node U exactly once. Okay, because we only visit it when the node changes status from undiscovered, oops, it's the wrong place. We only visit when we change the status of a node, when the node status is undiscovered, okay? But then when we visit, we change it to pending. So it will not be undiscovered again. So we'll never explore this node again. So every node is explored exactly once, okay? So essentially, you're going to call this procedure on each of the node in the graph exactly once, okay? And so that together with the initialization time takes order of V, okay? And when we explore all these nodes each time, we essentially spend the degree of this node. And when we sum it up to over all the degree of all nodes, that basically give us the the order of the number of edges, okay? Because visiting, looking at the out degree of a node essentially is the same as saying looking at the outgoing edges, okay? So for direct graph, that means each edge will only be visited once when we're looking at the starting endpoint. For indirect graph, each edge will be touched twice for each of the endpoints. Okay, so the total time complexity is same as the BFS, which is V plus E. Right? Okay, so in other words, this is as efficient as the BFS algorithm in terms of graph traversal. Okay, however, property speaking, since we are doing the steps first search, we keep going deeper and deeper. Unfortunately, from BFS, you cannot retrieve the shortest path information, unlike the BFS. Okay. Nevertheless, it turned out that there are still properties of the DFS algorithm, which we're going to talk about next time. Okay. And that's all for today.